guys, so let's do this problem of thermodynamics using interpolation. Interpolation is a skill that at some point it will be necessary for you to use. And I personally, it's not something that I would do all the time, but it's something that you will do at some point and you need to have the skills. Okay, so let's just do this problem regarding thermodynamics. So this is steam table. Okay, hopefully you can check this one out. This is H2O. Okay, and something is happening to this rigid tank. Okay, so what I want to put here is the initial state, and let's just check what things I have initially. So initially I have the volume that it's around 0.0 cubic meters, which is the same thing as what they are giving me right now. So 10 liters. I'm going to change this. Okay, so temperature at 1 is 100 degrees Celsius. That's something that you can see. And also, it's a mixture because you know they are giving you quality, and this is 1.123. Okay, so that's something that you know. And they are asking me out of this, okay, that after certain heat transfer, it's gonna reach to 180 degrees Celsius. And after that, they're asking me, okay, can you please calculate the heat transfer? And they are also giving me the answer. So maybe we'll check out if this thing is correct or not. Okay, so that's what we need to do. From the very beginning, you can write this. This is the first law, okay, for thermodynamic systems that are closed. Okay, so these are for closed systems. And maybe you now can detect that the work of the boundary work or the expansion compression work is zero because it's actually a rigid tank. Okay, so that's it. So if you want to know the Q, you need to have this guy. And that one is not very difficult, at least to propose. It's just the mass multiplied by the internal energy at 2, or the final one, minus internal energy at the initial state. Okay, so that's what you need to get. Therefore, I'm gonna try to get U1, U2, and M. Okay, so let's go to 1. Let's go to 1. So to 1, what you can see here is I have these two information, and that thing is very easy to get now. The B1 is gonna be equal to BF1, the liquid saturated part of the specific volume, plus the quality times the saturated steam minus the saturated liquid. Okay, so this is for the specific volume. And since I know at which temperature I should go in, so I'm going to tell you right away BF1 and BG1. And this one is 0.01043. And this was 1.6. I think I have it here, 72. Okay, so these steam tables that I have put here is not for that first part because the first part is really easy to get. Okay, it's not very complicated. It's for the second part. Okay, so with these two informations, these two fellas here, so you can actually get everything. So I'm going to put this then that B1 equals to, according to my calculator, 0.20657. Okay, so you should check out cubic meters per kilogram. Now let's just go to U1. Also, if you know BF1 and BG1, you can also go to 100 degrees Celsius in your steam table and then look for UF1 and UG1. And these guys are 419, and then 0.06. And this fell over here is 2,506, okay, kilojoules per kilogram. So I'm going to use this one in this equation. U1 equals to UF1 plus X1 multiplied by UG1 minus UF1. Okay, so you have everything in order to get this one, and therefore U1, if you can use your calculator, it will be the same thing as, hopefully I have it here, yes, 675.761. Oh my god, kilojoules per kilogram. So everything is known for the initial state. Therefore, yep, I actually have this one. You may be asking, why did you get this information? Nobody was asking you about this one. Okay, so why are you putting that? Okay, so one good way is that they are giving me the volume. So I know that volume one, it's already here, okay? So the volume one, and also if I know the specific volume at one, maybe I can get the mass, and actually I can get it because the mass one equals to the volume one divided by the specific volume at one. And since I have everything at this 0.01 divided by this information, which was 0.20657, therefore my answer for the mass at one, which will be the same one in two, okay, m1 equals to 0.04841 kilograms, okay, so a very small amount in this 10 liters of container. Okay, so that's what I have for the initial state. Not very complicated, I would think. Let's just go to the second state. So I'm gonna put this one here. This is 2. What I know is that this guy is 100 degrees Celsius and not much more. But now maybe you can see, if you are solving this type of problems, that you have T2 180 degrees Celsius, and you also V2 equals to V1, which equals to 0.20657 cubic meters per kilogram, because if the volume cannot change and the mass doesn't change, therefore the specific volume doesn't change, okay? So that's why I'm doing that. Okay, so with these two information, you need to check in which region you are. So that's what you're gonna do. And if you do that, you can do this graphically or not, okay? So let's just check that at 180 degrees Celsius. I'm not using the steam tables right now for that. You need to check that on your own. And you need to know that BF and BG are gonna be for 2, okay? So for the second state, not for the first one. Maybe they are not these numbers. These ones are for the initial state. Now for the BF2, I have here that at 180 degrees Celsius, I have that 0.001127. Meanwhile, VG2 equals to 0.19384. Okay, so with this, you can check where you are. Maybe this value will be here, compressed liquid, maybe it will mixture in the middle, or maybe it will be at your right, which is superheated steam. In this case, it's barely superheated. So this one is my saturated steam, and this one, it's a little bit higher than that. Therefore, it's superheated, not very, very superheated, not really overheated, but a little bit more than that. Okay, so you need to go to your superheated steam tables if you can. So that's what I have put here. So these are my superheated steam tables, okay? And maybe you can see now the problem. If I know the pressure, if I somehow I know the pressure, I can go into those ones, but I do not have the pressure. I just have temperature and specific volume. So my first way to do this problem is by an approximation. Okay, so I'm gonna put it here. This approximation would be something to do fast as an estimation, and maybe I don't want to deal a lot with this. So this is what I would do. I will put all my, every time that I see 180 degrees, I'm looking for 180 degrees Celsius, and I'm also looking for 0.20657. That's my specific volume. So maybe you can see that I do not have 180 degrees Celsius. That's something that I could be confused. Okay, so I'm gonna take the best one that it's not 180 degrees Celsius, which is 200 degrees Celsius. It's the closest one, right? So I would put 200, and there is 200, and there is 200 here. Okay, so in those 200, which is my best guess after 180 degrees Celsius, I would try to look for 0.2065. And to do this thing short, maybe you can see here, you can see that at 1 megapascals, I have 2 of these ones that are really close together. This one is not 180 degrees Celsius, but at least the closest one. And this one is not the one that I'm looking for. It's pretty close. Okay, so I'm gonna say, well, you know what? That's the one that I'm looking for. It's something that I can estimate. And I'm gonna say, well, you know what? I'm gonna take the 1 megapascal. They are not asking me the pressure. They are just telling me, okay, can you find U2, the internal energy? So yeah, I already find it. So 262. So I'm gonna put it here. So U2 equals approximately to 2000 to 0.3. Okay, so 0.3 kilojoules per kilogram. Okay, so if I do that, I'm gonna write this right away. I already have everything in order to put this one here. You have the numbers there. And if you do that, this is the same thing as Q because the work is not there, it's 0. Therefore, the work in this case equals to 94.231 kilojoules. Okay, so this one comes from the approximation, which is in green. Okay, and it's pretty close. It's not that bad. Okay, it's 1.8% out of the 92.5 kilojoules. So if you are not interpolating, it's not that bad, okay? But at some point you will need to interpolate. So let's do interpolation. So for the interpolation, I have already prepared a table because you need to interpolate several times. This is a thing with interpolation. Maybe it's not just one time. There's much more than that, okay? So let me just grab another one and then I want to say, okay, 1. Let's just try to get something out of that. I'm going to try to get the B when I have 0.8 megapascals and temperature equals to 180 degrees Celsius. Why? Okay, so good question. Maybe you can check, I'm going to erase these ones here. Maybe you can check between 1 megapascal and 0.8 megapascals. Maybe you can check that. Okay, so I have this value and I have this 200, yeah, and I have this value over here. So it seems that between 0.8 megapascals and 1 megapascals, somewhere there, my value of V2, which I know, okay, is lying. So it's actually in between those two values. It's pretty close to 1 megapascal, right? Because it's kind of almost this one. But okay, so this information, remember, is at 200 degrees Celsius. You don't have that one. Okay, so what I have done here is that check 1 megapascal. So for 1 megapascal, this is what I have here. So for 1 megapascal, I have 180 degrees Celsius. It's almost 180 degrees Celsius saturation temperature. So this one is saturation at that 1 megapascal. And I also have written here the volume, the specific volume is this 19,437. And I also have written this for you, okay? So that one is saturated, the saturated part. And at 200, I have also written this one and this, this one and this one, okay? So that is my information for 1 megapascals. And I'm gonna write it here, what I have done for 0.8 megapascals. This is, everything is coming from the table. Take a look at 170 and 200. What about 180? That 180, I did it. So let me just take a look at this 170. This 170 is because the saturation part, this one over here, it's at 170 degrees Celsius when it is at 0.0 megapascals. Okay, so what I have done here is that at this also saturation temperature, 170, I have written the specific volume here and the internal energy there. So that's for the saturation. And then the table shows me the one for 200. So it's actually showing me for 200. And I have also written the specific volume and the internal energy. So what I need to do is to prepare everything at 180 degrees Celsius. So I need to interpolate. The first thing that I need to interpolate is this fella here, this one here, which is actually getting the specific volume at 180 degrees Celsius and 0.8 megapascals, okay? So I'm trying to put in a sandwich this value that I don't know yet, but I will get it for you, okay? So this one, I don't know, but I have this bread and this also bread from that sandwich. And I also have this bread and I also have this bread for the sandwich in the temperature. But look at this, the ham or the ingredient, I don't know, the meat in this sandwich, I already have it. So what I'm gonna put in interpolation, mathematical expressing this is this. It's not very complicated, okay? But you need to have a lot of information. So I'm gonna put here the V that I don't know, this one I don't know, minus, let me just, I'm gonna take 0.24035, okay? And then 0.26088 minus 0.24035. Okay, so and in this part I'm going to put the temperatures, and the temperature is 180. So this one corresponds to this value here. This one should have its temperature here minus 170. okay, because this is a specific volume for that 170 degrees Celsius. And I'm going to put here the 200 minus 170. Okay, so this one corresponds to this one for the specific volume. It should be the same. So if I'm going to clean this one up, maybe you can see what I have done there. Okay, so in this case, you are having this a specific volume. So this specific volume, which is at 0.8 megapascals at 180 degrees Celsius, it's actually equal to, if I'm not wrong, 0.24719. This is not solving the problem. I'm just building the problem. So this is my first part. I already have something that I need, okay? Now, after that, I know that you are looking at several numbers here that I have already solved, but I'm going to show you how I have done it. Now, let's just go to another one. Let's just put 2, okay? So 2, another interpolation. Now that I have these specific volumes at 180 degrees Celsius, which is a good thing, and I already have specific volumes at 180 degrees Celsius, okay? And these two things happen at this 1 megapascal, and this happen at 0.8 megapascals. Now, the thing is that, okay, can you have something else? Is there something else that you can do? And I would say, yes, you know what? Now I'm going to try to get the pressure. I'm going to try to get the pressure. So get the pressure at these conditions. At 180 degrees Celsius, okay, I'm going to use the 180 degrees Celsius because I have this information here and this information here, and the specific volume of my data. So the specific volume, which is equals to which is V2 actually, this is 0.20657, okay? So what I'm trying to do here, okay, what I'm trying to do here is that maybe I can get the pressure where this value of a specific volume and 180 degrees Celsius is actually happening. This is actually what should be happening here at 180 degrees Celsius, and V2, I want to know the pressure. So I will use interpolation to know the pressure. So this is what I will write. I will write this. Hopefully I can get you through this part. So P, the one that I don't know, minus 0.8 divided by, P, I already have it. So I have 1 megapascal, 1 megapascal minus 0.8, okay. And then here I'm going to put specific volumes. All of them happened at 180 degrees Celsius. So this is what I'm going to do. Whoop, a bigger one minus. This one should correspond to this one because that's the pressure that I'm looking at, that precise specific volume. So 0.20657. And then the specific volume at 180 degrees Celsius at 0.8 megapascals. So this is the one that is happening here at 0.8 megapascals and 180. I should put my 0.24719, which wasn't in the table. I need to build it. Okay, now for 1 megapascals, this one is 0.19437. This is the one that I'm looking for. 437 minus, again, 0.24719. And you need to use a calculator in order to get it. It's not very difficult. The first thing that you need to do is try to do this one first, then multiply by this one, because this one passes multiplying, and then add or subtract this value that you're having here. And that's it. So the pressure that I have here, I'm going to put it here. So the pressure that I have here is it's actually this one. I don't know what I'm looking for. So 0.9538 megapascals. So that's the one that I have. What's this pressure? This pressure is the one that is in that container, in this tank, at 180 degrees Celsius, and with the specific volume of 0.20657. Okay, so I just got from the steam tables interpolating twice, okay, the pressure that this tank is on right now. Okay, they weren't asking me that. Oh my God, yeah, you're right. So what I need to do is to get the internal energy. And you may be asking, why didn't you do that the first time? Well, because I needed to get to this part that I need to get the pressure. You will see why. 3, okay, so again, let's just go to 3. Now, get you, okay, get you when or at the conditions when the 180 degrees Celsius. So I want this 180 degrees Celsius, this one here, okay? And pressure equals to 0 megapascals. So if you remember, if you go to this table and go to 0.8 megapascals, let me just erase and clean this a little bit, but maybe you can see that I have this line, saturation line is 170 degrees, and the other one is 200 degrees. Therefore, I need internal energy that happens to be at 180 degrees. So I need to build that. And this is what's happening in this table right now. So in this table, whoop, I need to get this 180 degrees Celsius and at 0.8 megapascals. This one is the saturation part. This one is 200 degrees Celsius, and this one, I don't know. I know that you are looking at it, but this is how you got it. This is how you're gonna get it. So U minus, and you need to put another one. So let me just go a little bit. So you're gonna put, I don't know, which one should you put? It depends. It actually, you can do whatever you want. So what I'm gonna do is this. I'm gonna put this one does me 2,500 minus 2,576, and then use the other one. It's like the sandwich, right? So you are putting a sandwich, the one that you don't know yet. So you're gonna put 2631.1. Okay, it doesn't really matter which one you put first. Maybe you could put here, instead of the 2,500, you can put the 2,600, and it doesn't really matter. Okay, but you need to put it correspondingly. Therefore, at this place, you need to put, oh my God. So what you're gonna put here is that this one corresponds to 180 degrees Celsius, 180. This one was 170, right? And this one was 200, and then this one was 180, 170. Okay, so that's what I'm doing. And everything about this information, it's happening at 0.8 megapascals. Okay, so now if you do your calculations, this is you at 180 degrees Celsius, 0.8 megapascals. And if you do the things correctly, I think I have it over there. So it's 2,594.37. This is what I have, kilojoules per kilogram. Okay, so now we are getting there. This is still not the YouTube. This is still not YouTube. Why not? Well, because it's happening at 0.8 megapascals. And I need an internal energy that is happening at the point where we're at this pressure, at 0.9538 megapascals. That's the internal energy that I'm looking for. So finally, hopefully, so finally I'm gonna put here 4, let's just put 4, get the internal energy at 180 degrees Celsius, and the pressure equals to 0.9538 megapascals. Let's see how that interpolation will look like. So the first thing that you need to do is you always do that. And at some point, you're going to put the ones that you know and the ones that you don't know. And at some other place, I'm going to put 0.9538 megapascals, because that's the one that corresponds to this one. And everything here at this place needs to be at 180 degrees Celsius. So I'm going to put here the pressure part, and the pressure part 0.95 minus, I think I put here the 0.8, but remember, you can put 1 megapascals, and I'm going to put 1 minus 0.8. You can put backwards, it doesn't really matter, okay? It's going to hold the same equality. And then I need to put you here at 0.8 megapascals, but 180 degrees Celsius. So that one here, I'm just going to show you that this one is the one that I just got. Okay, so that's what I needed to do that 180 degrees Celsius internal energy at 0.8 megapascals. So the one that I'm going to put here is the 2,594.37, that it's in black just here, okay? And then I'm going to put it again, this one over here, and then I'm going to put the one that it's at 1 megapascal. So at 1 megapascal and 180 degrees Celsius is actually this one. So 2,580, 2,582.8. Hopefully I'm putting the right numbers in the right place, and you don't have to worry about anything. Therefore, you, which is already U2, or the one that I'm looking for, because it's actually at the pressure that it's happening and at the temperature that it's going on, okay? So this one is actually equals to 2585.47. Okay, so how do you know you are correct or not? How do you know this is correct or not? One way to put it is that, well, so if this information is correct, it means that I'm closer to this value, 82 to 85, it's pretty close, than 94, right? So I'm closer to this value of 1 megapascals. And you need to see to look at the table, and maybe you can see that that is actually correct. It's pretty close to this one. I know that it's not 180 degrees Celsius. That one is not 180 degrees Celsius, but it's pretty close to the 1 megapascal information that the one at 0.8 megapascals. How do you know that? Well, look at the pressure that we got. The pressure that we got is pretty close to 1 megapascal. It's actually farther away from the 0.8 megapascals. So maybe this thing is looking in the right way, okay? So I know there's a lot to take in at this interpolation part, but well, that's the way you deal with it when you're looking at steam tables for certain things. Now that you have everything, it's just substituting stuff. Substituting stuff means that delta U needs to be equal to the mass multiplied by U2 minus U1. Remember your approximated U2. So this one was our approximation, this one here. So we use 2,622. Okay, it seems that it's pretty far away from this one. Okay, this 85 to 22, but in the next hundreds. Okay, so you need to go to 15 plus. Okay, 15 plus and then 22 plus. So you are kind of, I don't know, 37 kilograms away from your approximated U in the last part. So in this case, it's more accurate. And let's see if this thing is, well, you are really close or not, okay? So U1 hasn't changed. U2 is the one that you're looking there, and the mass hasn't changed. Therefore, my Q that I have here is actually equal to 92.45 kilojoules. So that's the one that I have. If you look at the result is 92.5. So yeah, well, yeah, so 92.5. Well, we are 0.05 away from that because of the numerical stuff that we have used. Okay, so that's kind of the idea. And we are actually really close to the approximated part. Or I should say the approximated part is closer to this one, okay? Because this one is the more correct. Okay, so that's it for me today. We just saw interpolation part. Take a look at this. It's a little bit confusing, but you need to do it step by step to know what the hell happened there. So I will see you later. Take care.